Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready. For real, get yourself ready this time. With a notebook, you can grab a pencil or a pen. Whatever you choose to write with is totally fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, as the title suggests, we have a half circle but a full send. This problem is not for the weak-minded, the lazy. So if you're ready to step up to the challenge, here we are. We're going to use techniques that are not present in calculus, although you could also solve this problem in calculus. The thing that makes this problem tough is that representations are so important. And you might not be used to seeing quadratic equations the way that you're going to see a quadratic equation today. But you need to start to get used to that if you want to be successful in AP Calculus or first semester calculus. So without further ado, give the problem a read. It's a pretty simple problem, honestly. I think it's easy to understand the visual representation, to understand what's going on there. But that does not make this an easy question by any means. So go ahead and give yourself about 12 minutes or so for parts A and B. And then if you're really bold, you can try to tackle part C. And you can give yourself maybe about 7 minutes or so for that one, 7 or 8 minutes. But when you're ready, unpause the video, join back, see how we did it here. All right. Now, looking at the problem, we see that a rectangle is attached to a semicircle along its longest side. So I'm just going to kind of sketch that out. And we'll say it looks something like that. Definitely not perfect. Let's see if I can do a slightly better one. That one looks a little bit better, I guess. And so the radius would be coming from here. That's going to be the radius. I put it in the wrong spot. But also that means this would be the radius, and this would be the radius. So notice that the diameter is like the span of the semicircle, and that's how long the side is. Meanwhile, we can just call this h. Why not? So we have the length of the rectangle is 2r, and the width, you might just call it h. All right. Let's look at some more description here. So for all of these problems, the total perimeter is 50 centimeters. We want to find the dimensions of the rectangle specifically. So we're looking for L and W. All right, we're given this nice constraint, 50 centimeters, and we want to maximize the total area. So we got to represent the perimeter in this equation. Notice that the perimeter is going to be 2h plus this length out here is going to be 2r. We're not going to add both of them because this is the one on the outside. We're not going to add this here because it's not on the outer perimeter. So we have 2r. And then we have this arc of the semicircle, which is basically a half of the circumference. So that's just going to be pi r. Perfect. Now we want to use the fact that the perimeter is 50. Now we can get an expression for h. Because if we want the total area would be the length times width of the rectangle, which is going to be 2r times h, plus half of a circle. So that's going to be pi r squared over 2, right? As you notice, we need h. So we have to use the constraint of the perimeter in order to find an expression for h. Let's solve for h. We can start by subtracting. That would give us 2h, and then we can divide everything by 2. So we're going to get 2 plus pi over 2 times r, and that is h. Now that's a little bit messy looking, but we're going to have to use that in the area formula. So let's plug that in now. The total area is going to be 2r times this h. And then plus we have pi r squared over 2. Alright, so let's go ahead and distribute this in. Pretty easy stuff. 50r. When we distribute the 2r in, of course it's going to cancel with the 2. That's nice. So we're going to have 2 plus pi r squared. But we also have pi over 2 r squared. So what can we do with this? We can treat it like a quadratic. It doesn't yet look obvious to a quadratic, but this is a quadratic in R. If we treat R like the x, we can put this in, ax squared plus bx plus c kind of format, but using R. And when we do that, what is our coefficient? Well, our coefficient is going to be pi over 2 minus 2 plus pi quantity. Not over 2. We're going to have to get a common denominator, though, for that. With r squared plus 50r. All right. Now, in order to find a maximum, and can we guarantee this is going to have a maximum? Well, yes, this is going to have a maximum because this is a negative. So when we have a negative leading coefficient on a quadratic, we get a parabola graph that's facing downwards. So it has a maximum value. We find that maximum value using the formula negative b over 2a. So this is about to get even messier. However, we're going to find the value of r, which produces a maximum for the total area formula. That's what we're after. What's the r value? Then we can use that to find the h value. Hopefully this works out fairly nicely. We'll see. Negative 50 over 2 times the quantity pi over 2 minus 2 plus pi. Yeah, that's actually very doable. So we're going to have negative 50. And when we distribute the 2, it just cancels under the pi. So we have pi minus 2 times 2 plus pi. And believe it or not, that works out with a little bit of fidgeting. So we get pi minus 4 minus 2 pi, which is negative 50 over negative 4 minus pi. We can take the negatives out of everybody, and we get 50 over 4 plus pi. Goodness. So it wasn't as ugly at the end of it all as you might have thought it was going to be. This is our radius for the semicircle, which if we attached it to a rectangle and had limited perimeter, this would maximize the total area. Now we can use our formula for h. Right, remember that the formula for h, well, I guess it doesn't matter what order I put that in, but just to stay consistent, even though 2 plus pi is the same as pi plus 2, y'all know that. This was my equation for h. So if I simply plug that in, it's not necessarily going to cancel the best that you would want it to, but that's okay. 2 plus pi over 2 times 50 over 4 plus pi. I would love to say that's beautiful, but it's really not that beautiful. So we're going to have 25 minus, and that gives us 50 plus 25 pi over 4 plus pi. If I really wanted to get a common denominator, I'm sure I could. So let's do that. We're going to end up with 100 plus 25 pi minus 50 minus 25 pi. Get some nice cancellation there. For a total of also 50 over 4 plus pi. Very interesting there. So these are the dimensions of the rectangle that are going to give us a maximum total area. And it's possible that this result is due to the fact that we have a circle attached to it. Usually when you have a fixed perimeter, the ideal is a square. But in this case, it looks like we get a rectangle where remember the length of the rectangle, we still need to finish that. The length of the rectangle is technically double of that. So it's 100 over 4 plus pi. And the width is 50 over 4 plus pi. So yeah, let's answer the question carefully, right? That's the whole point of this. Okay, now let's look at part B, which is saying that the area of the rectangle and semicircle are equal. Now, if that's the case, what we're going to be doing is saying that 2RH equals pi over 2 r squared. And so this is not necessarily tougher, but it is, different. It is arguably different. The way that it's different is that we know we don't need to find the area. We know that r is non-zero. Right? The radius of that circle has to be non-zero. So therefore, we can just simplify this equation to say that 2h equals pi over 2 times r. And therefore, h, in this case, is related to r as pi over 4 times r. So how do we solve for what r actually is? Well, we use our expression for h. We still have that expression that says, according to the perimeter constraint, 25 minus 2 plus pi times 2 plus pi over 2 times r, this still equals h. So now I have an equation that I can set equal to pi over 4r. And I would probably elect to try to cancel these denominators just so that the equation is a little bit easier to work with. And 25 is not a really difficult multiple. So if I multiply everything by 4, is basically what I'm saying, then we end up with 100 minus 2 times 2 plus pi r equals pi r. Not bad at all. So if we open everything up, we get 100 minus 4r minus 2 pi r equals pi r. We can add all the r terms on one side. I probably get these things over there so that they're positive. So 100 equals 3 pi r plus 4r, and then I can just factor out the r and divide this off, which is going to give me an r value of 100 over 3 pi plus 4. Very interesting there. Now, if that's the case, what is our h value? Our h value, using the r that we just found, is going to look like this. So let's go ahead and cancel 102. That gives us 50. And again, if we want to get a common denominator, we could totally multiply this by 3 pi plus 4. So we get 75 pi plus 100 minus 100 minus 50 pi all over the common denominator of 3 pi plus 4, which is going to leave me with, oops, I'm running into my other problem, which is going to leave me with 25 pi over 3 pi plus 4. That is the width of the rectangle, which means the length is going to be 200 over 3 pi plus 4. Wow, fascinating. Part C is a real doozy, you guys. If you were able to follow through this far, congratulations. Now it's time to really carefully consider what part C is telling us. It's telling us the total perimeter is equally split between the rectangle and the semicircle. So this portion and this portion have the exact same length, which means 2h plus 2r equals 25, and pi r, which is half of the semicircle, because this is not a full circle, it's just a half a circle, is also equal to 25. So how does that help us? Well, we have a very limited amount. We have 25 for both. So we just need to solve this system of equations. It's actually a pretty easy system of equations to solve, because we can take the pi r, divide both sides by pi, and we get an expression for r in terms of no other units, actually. So r just equals 25 over pi. That's already set. Because the size of the circle is fixed, the radius must also be fixed. That only makes sense. We're giving a limited amount of string to make a circle. So you're going to get a fixed size half circle. And then based on that, we know that the rectangle is twice as long. So it's 50 over pi. Now as far as the height or the width of the rectangle goes, this is simply going to say 2h plus 50 over pi equals 25. And this is very easy to just do some moving around, right? We can just subtract both sides by 50 over pi, divide both sides by 2, and we get that h equals 25 minus 50 over 2 pi. So did I kind of over scare you a little bit with part C with the star on it? Yeah, I sort of did. But if you were diligent enough to go this far, that's kind of the whole point of this video, right? So a few concepts there. We saw a quadratic equation appear that did not obviously look like a quadratic equation. I mean, if this obviously looks like a quadratic equation to you, congratulations, you're very sharp. You're at a higher level than I would say most people at your current math level that are going between pre-calculus to calculus. It's going to become key for you to be able to identify quadratic structures like this and work with them for when we have maximums, when we have minimums. And even though in calculus you're going to learn some great techniques for dealing with tougher functions, it doesn't hurt to be fresh with the basics. In fact, everyone could probably use some brushing up on the basics. Okay, I think that's enough blab out of me. I'll see you guys next time.